Hi, everyone. Welcome to Foresight's Molecular Machines Group. Really, really happy to see you guys here. And thanks a lot for joining, everyone. I really appreciate it. I think, as I mentioned at the beginning of the year, but since there's always different people joining, just going to repeat it. This year, we're going to do a little bit of an updated program in the sense that we have our continued keynote lectures. This is one of them, in addition to more focused brainstorms where people get to really brainstorm on the long-term implications of their work and long-term opportunities that they'd like to collaborate on that they may not have the space to talk about in other venues. We're also planning our molecular machines workshop, and so I'll be in contact about that very, very soon. We have the virtual programming to keep us, I think, to keep us really engaged and have had that during COVID. But I think, as many of you know, here who's been to our technical workshop, that's where actually the work gets done. And so I'm super excited to welcome you back for one of those this year. And in the meantime, really, really, really happy to have two wonderful folks here, Leonhard Grill and Joe Lyding. And I'm really happy, for example, that Joe has been to many, many of our Foresight technical workshops already, so he knows a little bit of what's going on there. And both of them will be presenting, and we have a structured Q&A afterwards. Usually what happens is at these meetings that we run out of time to take all questions. So I implore you to ask them early if you want them to be heard. But for now, I just really want to welcome Joe Lyding to start his presentation up. And Joe will be presenting on silicon-based nanotechnology. There's still plenty of room at the bottom. I'll post much more info on Joe here in the chat. I'm really, really happy to have you here. You've done fantastic work and you're a really wonderful collaborator at our conferences, and very excited to hear about what you're up to these days. I'll be in the chat from now on. Welcome, Joe.
Okay, well, Allison, thank you very much. It's a real pleasure to be here, and to been at these workshops before, and it's an honor for me to share the stage with Leonhard Grill as well. He's one of the pioneers in molecular nanotechnology. So, as you mentioned, I'm going to be talking about silicon-based nanotechnology. There's still plenty of room at the bottom, and I'll give you my interpretation of that shortly. So, but to start things off, this is one of the motivations for many of us in this field of STM and atomic and precise fabrication. Kind of the shot heard around the world was when IBM was written with xenon atoms on the nickel surface. At the time, I didn't even have a UHV STM, but I was thinking, wouldn't it be interesting if we could do something like this instead of at liquid helium temperature on a metal surface, at room temperature on silicon? So I started pursuing that avenue, and I wasn't alone. There were several efforts. At NIST, for example, John Bagata was showing that he could pattern silicon surface under ambient conditions to produce oxide patterns. Bell Labs and IBM were also hot on this trail. Russell Becker's group at young Russell Becker at Bell Labs was showing that wet passivated silicon 111, you could desorb hydrogen from that with an STM. Most intriguing to me was John Boland's work at IBM, where he showed that you could prepare this really nice monohydride silicon 100 surface. And I thought that would be the ideal template for this type of work, because if you remove the hydrogen, you don't change the surface reconstruction. So I set out to see if we could do something with that. So first of all, I basically followed his recipe and created a passivated surface. But then instead of just imaging it with the STM, I decided to try patterning. So in other words, increase the voltage between the tip and the sample to a high enough electron energy that you can actually break the silicon hydrogen bond. And here's an example of a pattern, 5 nanometer wide line of clean silicon that was created in that manner. And what's really going on here is this is done at 7 volts. And what you're doing is you get at that voltage, you're getting to the bonding antibonding transition where you can directly break the bond with a single electron. Even though it takes about 100,000 electrons to do the job, it's inefficient, but it's still it's the electron, the energy of a single electron gets the job done. So schematically, it just kind of looks like this. We excite from the bond with the anti-bonding potential. But interestingly, even in the early experiments, I was observing much higher resolution patterning at voltages below the bonding antibonding transition. And so the question is, what was going on there? And then Fade-Navoris actually explained this nicely as it's a vibrational heating mechanism. So what's happening in this case is you're actually exciting the silicon hydrogen vibration by inelastic coupling the STM electrons. And if that excitation rate exceeds the cooling rate by emitting phonons in the substrate, you can actually get to a hot ground state and desorb. What's nice about it is because it's at low voltages, you're basically operating the STM and tunneling and not field efficient, thereby the resolution can be much higher. And these are some patterns that were written, 3, 6, and 10 nanometer squares of clean silicon that were written in that manner. This led to the thought of, well, there's a lot of chemical contrast here. Clean silicon is very reactive. H-passate silicon isn't. So if you spray molecules on the surface, for example, they selectively decorate the clean silicon pattern. But even though the resolution is good, it's nowhere near atomically precise. So what we did is we improved on the technique a bit by detecting when desorption occurred, stop the patterning, and there, in that manner, you could start creating arrays of single dangling silicon bonds. And here's an example of one. And STM spectroscopy shows that it's metallic. There's several. Interestingly, you can make a dangling bond wire. It's essentially a metal wire. But if you depassivate dimers or 2-dimer rows, it's semiconducting. So there's an interesting electronic structure going on with the surface that you can play with. And you can make templates for absorbing molecules. For example, these are copper phthalocyanine molecules that have been absorbed, in this case, onto single dangling bonds. So, in any event, this kind of set the stage for a number of groups to do some really, really interesting things. Bob Wokal at Canada has been making some really interesting QCA structures. And of course, everyone knows about the Michelle Simmons work at South Wales trying to make quantum computers, and she made this single phosphorus atom transistor. Really, really cool stuff. There have also been some technological spin-offs from this work. For example, John Reinville and Zyvex, they developed their Zyvector, which is a lithography system designed not just to do this lithography, but also to correct for creep and hysteresis in the piezo scanners. So that it really makes a big step towards atomically precise. In fact, John is a big fan of its atomic precision, and he views that, moving in that direction is just like it's analogous to when electronics move from an analog to digital. He sees digital matter control as kind of the same type of a potential revolution. I agree with. Another spin-off of this work is the tips that we've developed for STM. We found that the process to make them makes really good tips for semiconductor probing. So we formed a company to do that. And yet another process that we saw was that if we took the hydrogen passivated silicon and replaced it with the deuterium passivation, the deuterium, even though the bonding energies are the same, it's about 2 orders of magnitude more difficult to desorb. And it's just because the mass of the deuterium is twice that of hydrogen. And what's cool about that is, let's get through here, is that I had this realization during conversation with my colleague Carl Ness that there's this analogy between hot electrons and a silicon transistor desorbing hydrogen at the gate oxide interface. And what would happen if that gate oxide were replaced by deuterium? Because when those dangling bonds reform, the device operating parameters switch, shift, and once they shift by a few millivolts, the transistor fails. So we thought, well, maybe deuterium would withstand that hot electron and solid interface, just like it does in the STM. So we tried it. We got some CMOS chips from Bell Labs, and in fact, we saw factors of 10 to 50 lifetime improvement when we replaced hydrogen with deuterium, which IBM confirmed. And currently, IBM are global founders now, and Samsung, they're actually using that deuterium processing from this in their full-scale CMOS production. What I'd like to do now is shift from just patterning to more of heterogeneous systems where we want to combine, say, top down with bottom up. So let's take a look at some bottom up, and probably one of the best examples is Leonhard Grill. Hopefully talk elucidate this in greater detail, but he's really pioneered the work of molecular covalent self-assembly on surfaces where you get atomic precision by getting nature to make things for you in really, really clever ways. Very fascinating work. Another example is to try to make graphene nanoribbons, again, where there's a covalent self-assembly on a gold surface by Basel company. I found this work extremely inspiring, but what I wanted to do is figure, could we do something similar, or at least take advantage of some of this in some way that it would be compatible with silicon? These are metal surfaces. And immediately ran into a problem. That is, how can I get something onto silicon that maybe is fabricated elsewhere, but it's too big to evaporate? So we just came up with a very simple technique. We call it dry contact transfer. So in ultra-high vacuum, we literally stamp the material of interest onto the surface, and that gives us it gives us a clean interface between whatever we stamp on and the surface. So an example, these are single wall carbon nanotubes on hydrogen passivated silicon. They're normally in bundles, but they exfoliate during the stamping process. These are pieces of graphene on gallium arsenide that's cleaved in ultra-high vacuum. Again, you can see the cleanliness of the system. But I was intrigued by this paper that came out in 2014 from Alex Sinitsky at Nebraska. And what he showed is that another route towards making these graphene nanoribbons was by wet chemistry. And the figure I really liked in this paper is this one here, where I saw this vial number 5 of black powder. And I contacted him, and he sent us some of that. And my student, Adrian Radesha, stamped it onto the silicon surface, and we were able to see the GNRs on silicon. That collaboration is continuing now with, we have a MURI program. There's another, it's called so-called Mousebygnr GNR that's Abigail Berg has been looking at in my group. But now what we want to do is think about where do we go from here? And here's a cartoon that suggests that if we could put GNRs on a surface and wire them up with metallization and gate them, we might be able to make a CMOS, the equivalent of a CMOS inverter. So assuming that we can put the GNRs down, they're still not arranged in a way that we would like, but we can get a clean deposition of GNRs. What about the metallization? What can we do about that? So we've been working on that, and what we're doing is we're utilizing an STM-based metallization process where we dose the surface with a metal precursor, and then with the STM, we dissociate it to leave a metal deposit. In particular, we're choosing a carbon-free metal precursor so that we get a clean deposit. People have tried this with non-carbon, with carbon-containing CVD precursors in the past, and you get a very contaminated deposit. We have a capillary doser that in UHV is positioned right next to the tip sample junction for this work. Here's an example of writing a line across the single wall carbon nanotube. The blue region is the semiconducting band gap of the carbon nanotube, and you can see where the line crosses the nanotube that you see this metallic behavior as well as a decay of metallic states. Another thing that's intriguing that you can do with metallization is the same thing that industry is doing with CMOS now. the channels of today's silicon transistors are undoped because dopant statistical fluctuations in dopants would be too much for the small size of today's devices. So what they do is they use a work function of the metal gate to actually induce N or P-type behavior in the silicon channel for make CMOS. And here's kind of a fun experiment we did where we wrote a feature of happening by board, which is very low work. It has like 3.5 eV work function. We wrote it over here next to a carbon nanotube. Here's the spectroscopy on the nanotube. It's just the gap collapses at the end of the tube, but the rest is just sort of a, just over 1 eV gap. And then what we did is we actually pushed the carbon nanotube with the STM tip. So it just draped over the happening by board. And you see this strong band bending where it goes from P-type to N-type, and it actually becomes degenerate metal at the peak of the crossing point, just because of the work function difference. Happening by board is about an EV lower work function than the carbon nanotube. And interestingly, when we push the nanotube back off, the semiconducting gap snaps back again. This is the end state, and then this is a silicon substrate outside of the nanotube. We're not seeing if we can move this a little bit further. Here's a work in progress. This is just a week or two old, where we're writing at poor resolution here, but there's a graphene nanoribbon here, there's one here. And what Pin Chow and Hung Yi have done is they've written happening by board contacts that cross the ends of the nanotube. So we're talking about something that's about a nanometer wide and just 20 nanometers long, pretty small. STM spectroscopy shows that the crossing points are metallic, where the happening by board is. Graphene nanoribbon has a larger band gap than the surrounding silicon substrate, again, which we expect. And these particular metal features are just a couple about 4 nanometers wide and 2.5 nanometers tall. Where we're going with this, and the experiment in progress now, is we're going to integrate this with these types of finger arrays that are made by EV lithography, where each adjacent finger connects to a separate electrode. So in this small quarter micron gap in here is where we're going to be transporting that experiment. So what I'd like to do is, just to maybe set up for some of the discussion is think about where can we go from here. We have, we've demonstrated the ability to work at the atomic scale, but there's a long way to get from there to, say, technologically relevant production levels. And this kind of reminds me of a couple of the past workshops. So, for example, in 2018, at the Foresight workshop on molecular machines, integrated molecular machines, we thought about using DNA as a vehicle, DNA origami as a vehicle for this type of assembly, where perhaps it would be placed in registry on a silicon substrate, and then the self-assembly within the DNA could be used for something. In fact, one of the funding programs I'm involved in now, it's a MIRI program. It's exactly that. It's actually using DNA assembly to create graphene nanoribbons, whereas the GNR precursors are built into the DNA structure, and then they're put in a desired sequence. So that could actually map onto this type of thing. Another workshop previous to that in 2016, this one was, we were thinking about ways of making a template that could then be like used as a stamp to, perhaps stamp some desired nanostructure onto a surface. So you'd use a precise technique like STM once just to make a template for nano imprint or stamp that would then be used to parallel process. Interestingly, if you look at tools like EUV lithography, like the ASML tool, that most recent one, they are really approaching 1 nanometer scale resolution. And what that kind of makes me think about is you don't have to make something atomically precise to do atomic precision. So, for example, if you were to create a rectangular opening in say, an oxide layer on top of a gold 111 surface, um, even if it wasn't perfect, if you introduced precursors to make, say, for example, a graphene nanoribbon, only a digital number of those molecular precursors would fit in that pattern. And they could self-assemble into a graphene nanoribbon that's precise, you know, essentially atomically precise. And then this could be happening in parallel over an entire wafer surface. Right now, this ASML2, I think, will process 135 wafers per hour. And like I said, it's projected to get to 1 nanometer resolution. So that may be a way to sort of transition from doing things, on the scale of an STM to doing things on the scale of today's wafer production. So it's kind of an interesting thing that it's really coming along fast. Well, what I'd like to do is end here, and I'd like to acknowledge my current group. Abby's working on DNA guided GNR fabrication. Ben Chow and Hung Ye are making the GNR devices. They're also making superconducting devices. Steve Kolitskowski is working on STM guided GNR nanofabrication, and Amte's working on GNRs and 2D charge density wave systems. And Gang Wang and Brendan Woolen are working on, we've developed a 3D printed carbon nanomaterial process that they're working on. You can see our funding and our collaborators, and thank you for your attention.
Wonderful. Thank you so much. Really appreciate it. That was really wonderful walkthrough, I think, of the entire space. In the absence of immediate questions, what I would love to do is have Leonhard go next, and then the past few minutes can then be used for a Q&A, perhaps even guided by the challenges that both of you already submitted. So that'd be wonderful. Leonhard, please take it away. Thank you very, very much, Joe. That was a really, really wonderful start.
Okay. Can you hear me?
Very well.
Okay. And can you see the presentation too? Yeah.
Yep.
Okay. Thanks for having me. Thanks for the invitation. Thanks to Joe. He very nicely presented the field and what is possible. I want to show you some results from my group, what we have been doing with manipulating single molecule surfaces. And typically these molecules have a function. There are switches or motors or others. And we try to control that and try to understand what's going on there. So we're working with STM. Joe introduced the method already. You can see here 2 STM tips. That's a very particular setup. Normally it's just one, of course. And working at ultra high vacuum, everything extremely clean, almost like the scheme here, low temperatures to keep everything stable. The first example I want to show you is molecular switch. So that's a molecule that has at least 2 states. We can transfer the molecule between the 2 states. As a benzene is a prototype of such a switch, having a trans and a cis isomer. We studied these molecules on the surface. So that's the molecule we've studied. It has 3rd butyl groups here. You can see them in the STM image. That's a single molecule in the trans state on the surface. And we can play with this molecule and switch it directly on the surface. We find islands of these molecules. So that's a single molecule, for instance. So that's an island of many molecules. Then we apply voltage pulses in the center and see whether they can be isomerized. And as you can see here, one image after another in the movie, the bright lobes pop up. These are single cis isomers coming up, and they also switch back like this one here, for instance, from the cis now to the trans state. So we can do reversible switching of the molecules on the surface. We can learn a lot about the process that's going on. I won't go into details of this, just to tell you that the switching is highly controlled. It changes a lot if we slightly change the chemical structure of the molecules. If we attach, actually not us, but our chemistry friends, Stefan Hecht here, they have attached a methoxy group here at the end of the molecule. For us physicists, a rather small change. In chemistry, that makes a big difference. We induce asymmetry in the molecule. Now a single molecule appears at different height, a bit brighter here than there. We know where the methoxy is. If we deposit the molecules and look on the structures, we now find not only one structure, we find 4 different structures. This is because the molecule has dipole moment now, and these dipole moments can rent in different ways with respect to each other, and therefore they form these different structures. This is something that can be controlled with temperature, and if you do not have a microscopy image, it might be difficult to understand which one is present. And that's very important because they do show different switching properties. That was a big surprise to us when we did that. So what we did was we take an image like this one here, rather large image now, with an island in structure 1 and a huge island in structure 2 and 3 as labeled here. Now we apply a voltage pulse in this point here with the cross. And we thought, okay, they would switch like in the movie before, more or less, but they didn't. The surprising result was that no molecule ever switches in structure 1, no molecule ever switches in structure 2, but they do switch in structure 3. And they also switch in structure 4, by the way. So they're all trans isomers, they're all planar on the surface, but the local surrounding defines whether they can be switched or not. And that changed our view of the field, because it means if we have, let's say, the wrong assembly on the surface, let's say this one, number 1, we never see any switching. We would go to the chemist and say, please give us a new molecule. These do not switch on the surface. This is wrong. So every tiny detail of the surroundings is very important for the function of the molecule. We can go even further. We had this switching pattern here. We thought, okay, that looks like almost a pattern, like a lattice. Let's switch many of the molecules in the island. If we do that, we find lots of cis isomers. Every lobe is one cis molecule now. In between, there are the trans molecules. They're darker because they're flat. We can plot a switching lattice, as we call it, on top. And now we measure how likely is it for every molecule to switch in this assembly. We quantify this. So we have 6 molecules in a unit cell. That's a unit cell, one cell here. And number 1, the corners, they have a probability of about 80% or more to switch. All the others are below 5%. And that was a big surprise, because it means parallel molecules, all trans, very much the same, have a huge difference in the switching, number 1 and number 2, just depending where they are. So it's the surface plays a big role. It acts as a template. It addresses some molecules to keep their function, to switch, while the other ones are not allowed to switch anymore. So the surface does much more than just being, a support or a layer. It really defines the function. We tried to confirm this interpretation, because it could also be a cascade effect. You switch the first one, the others follow. To confirm that it's really the surface that does all this, we did this, what we called erasing reswitching. So we started with this surface area with a number of cis isomers. We erase them. That works nicely. So we go back to the trans arrangement, all the trans, the very same area. Now we plot the lattice on top, and now we reswitch them. The question is now, would the new cis isomers appear on the very same lattice? If it's a surface, they must do that. It's defined once and forever. And they truly do that. So we reswitch them. We find the cis isomers only on this lattice. We erase them, reswitch, erase, reswitch, and so on. And once and forever, the surface as a template defines the function of the molecules, which is a strong effect if you consider what molecules do. They're not just isolated entities. They go together with the surface, of course. Another type of molecular switch is based on proton transfer, tautomerization. So this is work from Gerd Meyer at IBM or Johannes Barth in Munich. You can have proton transfer within the cavity. That's an important process in chemistry and in biology. And we can follow that in STM as shown here and also there. So the hydrogen moves from one side to another in the cavity. We came up with a molecule that actually Takashi Kumagai from our group introduced. It was synthesized by Jacek Waluk in Poland. Porphysine, I didn't know that before, to be honest. This has a smaller distance here in the cavity between the nitrogens, so a stronger hydrogen bond and a more efficient tautomerization. That's the only detail, okay? It's just more efficient in tautomerization. If you put this on a surface, copper surface in this case, we find the molecule in this crescent shape. We know from theory, Mats Persson in Liverpool did that. We know that this is now this tautomer. The 2 protons are on the left. We also find it in this shape, then now the 2 protons are on the right. The white lattice is the copper surface underneath. So we know exactly where it's sitting. If we scan at low voltages, nothing happens. Everything is very stable. Like here, if we scan at higher voltages, we start to switch the molecule. So it changes appearance while we're scanning here in lines, horizontal lines. That means what we do is we switch between this tautomer and that tautomer. So we switch between this appearance and that appearance on the way while we're imaging. That's why the molecule changes the appearance here, as you can see. We can go higher with the voltage. The switching becomes faster, higher rates. So the lines are fuzzier. And if you go even higher, we cannot see the switching anymore. It's just a ring. Okay, it's too fast for our imaging.
Now, you mean that as you are rastering the image, it's switching, and that's why you get these horizontal.
Exactly. So here, for instance, you can see that maybe up till here, it remains in one shape, the left, crescent to the left. Then it switches. You can see the crescent to the right, back to the left, back to the right. So going back to this case, you switch between these two images on the way while you're scanning. Okay, does this answer your question?
Yes, perfect.
Okay. Now we can quantify this a little bit. So the switching rate, what does it do? And the typical way to do that in STM, maybe this is not so familiar to you, but it's very typical of what we do. We place the tip in this position, we keep it in this place, no scanning, and we just switch the molecule. That means we bring it from the state in which this is the bright part to the other state where that is the bright part. In other words, the current jumps up and down and up and down and up and down as it switches. That's the current as a function of time. You can see this telegraph noise, as we call it. So it's switching between the two states all the time. Now we integrate that. We just calculate how long was it in that, what we call the high state, the red one, or the low state, the blue one, and we get this one. Now, if you want to understand the next two slides, that's important to understand that we know how long is it in one of the two states, and that's, of course, a measure for the rate between the two states, okay? If it just goes in one direction, it's just one occupation, nothing else. This is just the scheme, what's going on. Now, we can measure this. We find the 60% to 40% ratio. We can discuss this if you want. It's not so important now. If we place the tip rather far away, low set point current means the tip is far away. Now, if you approach the tip towards the molecule without touching it, it's just in the vicinity. Surprisingly, this changes a lot. So just because the tip is somewhere close to the molecule, the switching rate changes. The molecule knows that there is something around. And we thought that's very much an STM manipulation thought. Can we do this with single atoms? So we started with this situation here. That's a molecule, that's just a scheme. We measured again these PL, pH, 60%, 40%. And then we place a single copper atom right in the vicinity of the molecule, like shown in the scheme here. Nothing changes, same rates. We move the atom somewhere down here, nothing changes. Now we go a little bit closer with the atom. If you place it here, you can see that the rates change. Even though the distance is rather large, it's almost 1 nanometer, and the atom is there, and the molecule knows this. The molecule knows it and changes the proton transfer in the cavity, even though there's just one atom in the neighborhood. We can go further, place it here. The rates change even more. So we make the high state more preferable now over the low state. And if you place it very close, there is no high state anymore, only the low state. The molecule doesn't want to be in the high state. So the switching is controlled by this atom, which is just in the vicinity of the molecule. The reason is this came from theory. We couldn't answer this question. We didn't know what's going on. Again, Mats Persson did that. The reason is that you deform this double potential well. So this is without an atom. It's of course degenerate, no difference. But if you place an atom on the left side here, the molecule is attracted by the atom and likes to stay towards the atom, which is more to the left here. So these two nitrogen atoms have lone pair electrons and they want to sit over the copper atoms. While the low state is the opposite. Now we are in the other tautomer and these two nitrogen atoms want to be over the copper atoms. But if it's attractive, this minimum goes down and accordingly, the high state becomes more likely. If we place the atom even closer, then it's repulsive. Now the molecule would like to stay in this state, go away from the atom. So this state is preferred and that one goes up in energy. That means there is no high state anymore, only the low state occurs. Okay, that's what you can do in this particular case, not always, of course, with switches. So the surroundings play a big role on the function of the molecule. A typical molecule, in particular for this Foresight group here, of course, molecular motors. We're also studying these. We're getting them from a good collaborator, Jim Tour at Rice University. He implements this Feringa motor from Ben Feringa into these molecules that are called nanorodsters. So they have two wheels, adamantane, and this axis. We want to understand what's going on in the motor there. We compare them. That's an important thing to do because it's very difficult to understand what's really going on in the motor. We compare them with similar molecules, at least for us physicists, that are very similar but do not have a motor. Okay, they have something else here. So whatever the motor does, this should be absent here because there is no motor in these molecules. We deposit them on the surface. We see these structures. So these are single molecules here. There are small islands of molecules. These are two molecules. You can see they consist of the two wheels plus the motor. It's not so important here. Now, we want to drive them remotely with light. That means what we have to do is we have to image them, as shown here. Then we track the tip by millimeters far away that we can illuminate. And then we go back. And the challenge is now we have to find the very same molecule again. So small shift laterally, only nanometers, with a huge vertical approach of millimeters. And then we compare before and after. If we do that at low temperatures, 5 Kelvin, nothing happens. So apparently we do need some temperature to induce the process, which is part of a Ringer motor. There's this helix inversion step, which is thermally induced. Now what we do here is we take an image before, we retract the tip, we find the very same area, you can see that here, and then we subtract the two images. So this is the difference image, and whatever is black and white was a change in the two images. If there is no illumination, you can see the molecules moved a little bit. That's because the temperature is 160 Kelvin. If we apply a laser in UV range, 266 or 355 nanometers, we see larger distances here. So the light does something to the motors. I must admit that the distances are a bit disappointing. They were also disappointing for us. We hoped they would move, 100 nanometers or so, but it was only a tiny effect, unfortunately. That's something we're currently working on to get this better. So in order to understand what's going on, we try to quantify that by two parameters. The first one is the so-called hopping rate. The hopping rate tells you how many molecules have hopped or moved per second. If you plot this hopping rate now for the different cases without light or 3 different wavelengths, there is no difference. The only difference comes from temperature, okay? Blue, red, green, that's obvious because the more temperature you deliver, the more diffusion you get. But nothing happens with the light. So the light does not change the number of molecules that are moving. But the number of molecules that are moving does not tell you anything about the distance that they're moving. So we looked on another property, which is the distance, or which is a parameter that is related to the distance, which is called the tracer diffusion. This comes from the mean square displacement. Let's say it's a measure for the distance. If you plot that one now, we see almost no effect here for the high wavelength, 635, but we do see a rather strong effect for the UV light. You see it here also in the factor 2 or 3 higher than the other one. So what happens is the molecules, the light doesn't increase the number of molecules hopping, but it increases the distance. It means the molecules that are moving thermally, they get another kick from the light to move a little bit further than they would do without the light. That's quite interesting. It tells us about something about what's going on with these motors when we trigger them on the surface. In order to be sure that this is the motor that's active and not something else that is photochemically exciting the molecules, we compared it with this control molecule without any motor, and you do not see any effect there. So it's truly the motor that is triggered with the light, and this causes larger distances. I do not say, that's important, that it's a propeller-like motion like we wish it was. We do not know. Maybe it's just a flapping, a bistable thing that increases more diffusion. But in any case, it's the motor that is wavelength sensitive and therefore triggers the motion of the molecules. Okay, last part of my talk about this molecule. Joe has very nicely introduced with kind words our own surface polymerization. We have done this with these molecules that are wonderful molecules, again by Stefan Hecht, Jutta Schwarz from Berlin, because we've used them for a variety of systems already, and they show nice behavior. In this case here, we have polymerized them. That means we put these on the surface, we heat them, so we take off the bromine, that's the weakest bond in the molecule, we dehalogenate them. That's the first step here. We get reactive sites, and then in the second step, when they diffuse, they form covalent bonds, and essentially a polymer. It's not an assembly anymore, it's one polymer. It was surprising to find that 15 years ago, because we thought the molecule would react with the surface rather than reacting with each other, but they do it very nicely. It's a very versatile process. It shows to happen with many molecules. In this case, you can see here very, very nice for our measures, very long polymers, 100 nanometers and longer. They run over the surface, contamination-free, without defects. That's a single polymer. You can see the lobes. Every lobe is a dimethyl here, and the arrows indicate the newly formed bonds, and you do not see any difference. So it's really a homogeneous polymer that you can grow. This brought us to the idea, oh, wow, this is a very cool thing. Leif Laferenz did that at the time. These are molecular wires on the surface. Can we pull them up from the surface? So get a situation in which you measure the current through a single molecular wire. And he did that, and he could measure IV curves through a single molecular wire. We know it's a single wire because we imaged it before and after. And you see the typical IV behavior when the LUMO comes in or the HOMO comes in of the molecule, use an increased conductance, and there is nothing here happening in the center there. And of course, the current goes down when you go higher with the tip because the distance is longer. You can also increase the length of the polymer in the junction and measure the current on the way. That means you measure the current or the conductance as a function of the tip height. And you see this typical decay. And this is very nicely what you would expect for molecular wire. The conductance shows an exponential decay with the length, something that is hard to measure with different molecular wires because you have to compare them, in a junction, different types with different lengths. Here it's smooth. You just pull it up and you measure it. And you can determine this inverse decay length. So what is the exponential factor here? This beta value. And we find this value, which is in agreement with theory. But not only this, we also see these oscillations. This puzzled us for quite some while. Why do they show oscillations on the way? And this comes from mechanical behavior. So while we pull it up, it's like a chain that we pull up from the floor, and one unit for the other detaches. And every time one unit detaches, we see a drop in the current because we make it longer. And this gives rise to these oscillations with this period that corresponds to the distance of 2 units. So we see electrical and mechanical properties. And very recently, these molecules that we have used for these molecular wires showed some other very different behavior because they move very nicely on surfaces. If we have these molecules now, it's a silver surface that's not too important maybe for the polymerization, but it's very important for the motion. If we have them on a silver surface, you can see again the 3 lobes, the 3 dimethyl, and at the end, you see the bromine here, okay? Now we can manipulate that. That's a usual standard thing with STM manipulation. We move the tip across and the molecule would rotate, okay? We find it afterwards in a different orientation. We can do this again, and so on and so forth. Like this fantastic IBM written with atoms that Joe has shown before. Now, with this molecule, something peculiar happened in some cases when we manipulate it, because sometimes the molecule afterwards appears as a stripe. It doesn't appear as a molecule anymore. It's something that is sort of continuous. And we can go further and further, make the image larger and larger. It's always a stripe that runs over the image. It took very long for us to understand what's happening here. And what is happening is that the molecule is moving very easily with a very tiny potential barrier over the surface while we're scanning. And if we take an image in atomic resolution of the surface, that's a silver surface, you see the atoms. We see that this is the direction of close packed silver atoms. So the molecules move along these silver atoms very easily on the surface, so easily that we cannot image them in a stable fashion anymore. And this brought us to an idea that maybe we can send them over large distances if they move so easily. We did a lot of experiments in our labs, and then we thought about the sort of ultimate experiment. Can we do this with 2 tips? Okay, can we send a single molecule from one tip to another in a controlled fashion? And we tried actually at different places, Ljubljana, Toulouse in France, and then Oak Ridge Lab in Tennessee. And in Oak Ridge, there was Mari Kolmer, and he's very talented and helped us to realize this experiment, to place 2 tips close enough together that we could realize this experiment. And this is what we did. So that's the scheme. We have a sender tip, the molecule underneath, and we want to send it to the receiver tip. We want to measure this, of course. To give you a measure how big these tips are, they're of course macroscopic, and even in an SEM, an electron microscope image, they're still large. We're talking about micrometers here. With the molecules, we're talking about the atomic scale, much, much smaller than what you can see here. You have to approach them very close to each other. That's really tricky and difficult. Very few people can do that. And then we image a certain surface area and define 2 areas, the sender tip area and the receiver tip area, okay? And now one tip scans only this area and the other tip scans only that area, nothing else. And now we try to send the molecule from here to there. So the sender tip area is imaged like this. We place the molecule here. We see this typical stripe. And the receiver tip area, of course, is empty before. There is nothing here. There's just this reference molecule down there. Okay, that's the reference molecule. That's without doing anything. Now we change the bias voltage of the STM tip. We make the tip repulsive. Here it is attractive. Now it's repulsive. At this point where the arrow points to, the stripe disappears immediately after we change the bias voltage. So it's black. The molecule is gone from this area. And most importantly, in the very same moment, instantaneously, the stripe appears in the other area. So we truly send in this moment the molecule from one tip to another, and it appears there, right in that moment. And this opened the question, can we measure the speed of the molecule? Can we tell something about the time it takes to move from one place to another? We did that by fixing the tip position. So the tip is now in a fixed position here, fixed position there. We just measure the current, and we should see a change in the current, of course, when the molecule comes or goes. And that's here. The black curve is the sender tip, the red curve is the receiver tip. You can see the molecule left the sender tip in this moment where there's the gray bar here, and the current goes a bit down, the red curve goes up as it approaches the receiver tip. You can zoom in. This is just an artifact. This is an inductive behavior of the tips because it changed the bias voltage. But what we can say is that within these 2.3 milliseconds, the molecule safely arrived at the receiver tip. Maybe it's even less. At the moment, we're trying to improve this type of measurement. So we can say the molecule moved 58 nanometers in 2.3 milliseconds. We get a speed from this value, okay? So we can measure the speed of a molecule. We can learn something about molecules, how they're moving on the surface. With this, I want to thank the people being involved. That's the group working here at the moment. We have a lot of collaboration with theory. Mats Persson was mentioned a few times. Chemistry, of course, we get these fancy molecules from different groups. Stefan Hecht, Jim Tour, Jacek Waluk made the molecule I've shown it today. Also experimented a few funding agencies, of course. And may I finish with, do I have 2 more minutes, Alison?
Go for it, please.
Okay, just some fun thing, because it was really a fun event. We took part in the first nanocar race that happened in 2017 already. The second event took place last March this year. We did not as well in the second one as the first one. That's why I showed the first one. So what was the challenge is the purpose was to move a molecule. That's our surface. These are molecules that came from Jim Tour. We had to start here with this molecule, then bypass this pillar, the second pillar as an obstacle, and reach the goal as fast as we could. This is really purely a fun event. But it was a very different challenge because normally speed is not an issue for us. You know, we take long time for every experiment. Here, we didn't care about anything on the side. Only speed mattered, only to be as fast as possible. Now that's a movie that shows you what we did. We started with this one. You will see a number of images while the molecule is on its way. You can see as it's moving down here, it passes the first pillar. Now it's approaching the second one there. And now it goes towards the finish line, and it reaches the finish line in the end after 1 hour and a half. Maybe this sounds slow to you now. It wasn't slow, really. Actually, we were surprised ourselves. We were quite lucky that everything worked so well. Many things can fail here. 150 nanometers is a long distance for our measures. And it was good enough to bring us the victory in that case. You can see in the other cases that people struggled, and this is because the process is very difficult. Many things can happen on the way. So we had about a speed of 100 nanometers per hour in that, and that was great to win that. Just to bring this into proportion, 100 nanometers per hour is very fast for us, but it's not really fast in nature. If you think about the growth of your hair might grow 0.1 millimeters a day, maybe, so 100 micrometers a day. That means 100 micrometers in 24 hours, 4 micrometers per hour, roughly. 4,000 nanometers per hour. We have 100 nanometers per hour here. So your hair grows 40 times faster than our molecules move. That's fantastic. So your hair would rush over the image if we could see that. But of course, this is done at 5 Kelvin, and your hair wouldn't grow anymore at 5 Kelvin. Okay, with this, I'm in the end. Thank you very much. I'm happy to receive any questions.
Wow, I love that you gave us an update on the nanocar race. Really happy about it. I've heard a ton about it, and we shared a lot actually in when it was just ongoing. So thanks for that. That was a really nice, cherry on the cake. Okay, wonderful. Thank you so much for both of your presentations. I know we only have 7 more minutes left, but maybe one thing that I would really, really love to hear you just briefly, perhaps to kickstart any discussion on, would be what is the number one challenge that you'd like to see others solve? So I know that both of you in advance to this have actually answered our emails with a challenge. Whilst, if new researchers or new folks when are interested and inspired by the work that you do and wanted to help it along in the field, then what is the number one thing that you would want to direct their attentions to? Perhaps Joe, you start, and then Leonhard, and if you want to make any comments also about each other's respective talks, feel free to do so too.
I think probably the number one challenge is making the systems even more heterogeneous, integrating not just metals and semiconductors and molecules, but getting insulators in there as well, like say for gate dielectric. I think that that's a type of problem that could be addressed by people like me and Leonhard and others. Because I don't think any of us are going to buy an EUV system, but so that would be my answer.
Should I continue, Alison? Yeah. I think, for these motors, for instance, I think it's known that they work, and there was the Nobel Prize for that 6 years ago. But I think what is still a challenge, and it would be fantastic to see if a motor molecule could be moved from one place to another in a controlled fashion, remotely. This is not by far not achieved yet. Can you define 2 places in space and say, go from A to B, and I trigger this externally? We are far away from having this. But of course, this would be the challenge if you think about building up structures atom by atom or all these ideas. You have to bring it in a position where you know where this is, and you have to control that. That's one thing with the motors. And the other thing is, as I've shown you, the surroundings play a big role in any of these functional molecules. And I think it would be great to take advantage of this in terms of cooperative effects. Can you assemble, for instance, motors, could be other things too. Can you assemble them and create a cooperative behavior of the motors that the sum is more than, or that the whole assembly is more than just the sum of its units, which in nature, this exists. We know cooperativity from nature, but it doesn't exist, or at least not with motors. It doesn't exist in the way as we would like to control that from the atomic scale. I think that's a big challenge. It would be great to have this.
Wonderful. Joe, Leonhard, any feedback on how to solve your respective challenges and comments? I just want to give you the space to
maybe may I comment on Joe's talk and also ideas. I think this is a very nice talk, by the way. Appreciate it a lot. I think you're perfectly right that the connecting the 2 worlds, the bottom-up atomic scale control and the top-down, which reaches amazing scales of 1 nanometer now, this would be fantastic. A pre-patterned surface, and then grow or assemble structures like the graphene ribbons in there. We have thought a lot about this too, because we thought that would be, of course, very cool. The problem we faced was that it's very difficult to get the cleanness from lithography that you need for atomic scale precision of your chemical reactions, whatever you have, because it's hard to get it completely free of resist and other molecules there. Do you have any idea of how to, do you think about systems that wouldn't be as dirty, or would be much cleaner, or cleaning procedures that could be applied there? Because I think that's really a key challenge there, that to keep the cleanness and at the same time to have this top-down patterning.
That's a very tough problem. I don't have a good answer for that. I haven't thought about it too much, but one might replace a traditional resist with something where, maybe like say EV patterning might remove molecules from a layer as opposed to just triggering a sensitizer. And if it were something like, let's say, for example, a porphyrin layer, we know that in UHV, you could probably sublime that off of the surface and avoid any type of wet chemical processing. So if there was something like that you could sublime off, you might be able to get down to a clean surface. But that's just sort of a vague notion.
Okay.
Yeah. I'd like to say, though, that, in literally, we've been working in a vacuum. I have, but when I started seeing the kind of work coming out of your group, what we could actually do, what can be done at that scale with the self-assembly, it's been incredibly inspiring. And I think what you're doing is really enabling to this entire atomic precision process. So it's been very inspiring to me.
Thanks.
Wonderful. I didn't know.
May I ask a question, Alison?
Sure, we have 1 minute. Go for it.
Oh no, not enough time.
Well, you can bring it up if you like.
Well, okay. So the idea of verifying that you can shuttle these molecules along these wires is one thing, and you've also shown that you can make, and it seemed surprising, although perhaps it shouldn't be in retrospect, that you can get these certain fragments to bond to each other rather than bonding to the surface. This is beautiful. Catalysis, enablement, fantastic. So now the question starts to become, this is all very laborious with these microtips and these scanning probes. Now, is there the idea here, maybe you guys are well on the way, but I'm just wondering, could you try and set up some sort of very simple, like two-dimensional machine, like a cellular automaton of some kind that would, go and grab something and stick it in and grab something else and stick it in and make on its own, shuttling around and making bonds with fragments, build some kind of pattern, thinking about scalability and sort of the intermediary between self-assembly and laborious STM-based assembly. Are you heading in that direction?
Maybe I start, but I think Joe can say a lot about that. So in terms of molecules, sure, you can bring molecules from one place to another with the tip. It's a bit time consuming, I would say, but people have done nice work. There's a fantastic work from Andreas Heinrich and Don Eigler, molecular cascades, where they built very complicated CO structures, and then these acted as calculators, as AND gates and OR gates. So I think you can do a lot. I don't think this is, industrially relevant at all. It's just too time consuming. You need something that works in parallel, not on a serial. But it could be done. The tip can move atoms, molecules from one place to another in a very precise fashion. It's just long in the way it goes. I think Joe knows more about the deep passivation, about what you do there, right?
Well, one thing that's intriguing is a lot of the stuff that Leonhard was talking about, you use a metal surface that actually catalyzes the reaction that forms these polymeric or DNR structures. So imagine that you had a surface where you just had really tiny islands of the metal catalyst, and that you could pattern these islands in a massively parallel fashion, say with UV lithography. And even though the islands may not be atomically precise, a digitized number of molecules would be at all that would fit on those islands, so that you would get an exact replica of the covalent structure that formed. That might be a way of sort of bringing in order and sort of bridging between this type of stuff that Leonhard and I are doing now and a massively parallel technological version of this.
Wonderful. We had at least a very brief reply to the question, and I think much more work to be done. I'm hoping that we can get to some of that again in our molecular machines workshops. Thank you so much to both Leonhard and Joe for presenting. It's really, really wonderful. Both of you have been awarded the Feynman Prize for your work, and this year we're really trying to make space and checking in where all of this fantastic work has has made progress into, and it's really, really, really rewarding to see. Thank you so much for coming here, sharing your work, staying 3 minutes over. We're really, really excited where this is headed, and we're hoping to weave together the threads of the individual presentations into something of like a long-term tech tree and roadmap of how to make progress. Thank you both very, very much for joining, and I look forward to the recording being published. All right, everyone. Thank you very much for joining today, and I'll see you for the next one very soon.
Thank you.
Bye.
Thank you. Bye-bye.
Bye-bye.
Bye.